Hey guys, welcome to the review of oxidation reduction reactions. And this will be for the electrochemistry chapter. Since we're going to be looking at the flow of electrons, we should probably remember how to do that with redox reactions. So oxidation reduction, we all lazy chemists call it redox reactions. It's a reaction that creates a flow of electrons. There's going to be two types of substances that we talk about. So one side is going to be a reduction. The other side is going to be an oxidation. You can't have one without the other. So if electrons leave one area, they have to go somewhere else. Or if they go somewhere else, they have to have a destination that they're going to. So there'll always be two sides of the reaction, one side or two types of substances. One will be reduced, one will be oxidized. And how do we choose who's being reduced, who's being oxidized? Well, we're going to look at where the electrons are going. So the substance that loses electrons during a chemical reaction is going to be the substance that's being oxidized. And I'll give you guys some creative ways to remember this in just a minute. And then if somebody loses electrons, that means somebody has to gain them. So the substance that's gaining electrons is a substance that is being reduced. How do we know who is gaining and who is losing electrons? Well, we're going to use something called oxidation numbers. So what I'm going to do in this review session here is I'm going to talk about how we assign oxidation numbers. So just remind us how those get assigned. And then we're going to look at a couple examples of chemical reactions and see how those oxidation numbers change across the chemical reaction. So rules for assigning oxidation states or oxidation numbers. This list is a hierarchy list. So the rules that are highest on the list are the most important. They trump other rules. The rules that are lowest on the list come after everything else. So first, the oxidation state of an atom in a free element is 0. So if you got something like iron, metal by itself, just Fe, that would have an oxidation state of 0. If you have something like a diatomic, so O2, Cl2, those are also examples of free states or free elements. So the oxidation number for O2 would be 0, or Cl2 would be 0. The oxidation state of a monoatomic ion is equal to its charge. So if you're looking at, I don't know, like a salt that's dissociating, so if you got NaCl becomes Na plus and Cl minus. What this is saying is the oxidation state of the monoatomic ion, so this guy right here, its oxidation number would be +1, and his oxidation number would be -1. So that's what that is saying. The sum of the oxidation states, if it's a neutral molecule, the sum of the oxidation states has to equal 0. And if it's an ion, the sum of the oxidation states has to equal the charge of that ion. So for example, if you've got a molecule like CO2, carbon dioxide. So this is a neutral molecule. So when I add up the oxidation state of carbon plus the oxidation state of each of the oxygens, that's got to equal 0. It's got to be neutral. If you've got an ion, something like carbonate, in this case, when I add up the oxidation states of the carbon and the 3 oxygens, the sum of those oxidation states has to be the same as the charge on the ion. So it has to be a 2+. So this summation is really what's going to dictate a lot of the nonmetals as far as oxidation states go. Metals will always have a positive oxidation state. So when in doubt, look at the number of valence electrons. That usually indicates what the oxidation state's going to be, but metals will always be positive. And then nonmetals will have oxidation states according to the following chart. So nonmetals are on the lowest on this hierarchy list. They're the least important, if you want to put it that way. So we always establish the oxidation number for metals, and then we go back and establish the oxidation number for nonmetals. So nonmetals, again, this is a hierarchy list. So fluorine is the most important in the world of nonmetals. And as we move down the list, we get less and less important. So fluorine typically has a -1. Hydrogen typically has a +1. And oxygen typically has a -2. The other three, man, you're just going to use what you have to determine the other three. It's likely that they will follow these rules, but I wouldn't even look at this part of the chart. I would just determine oxidation states for those guys according to what's on the paper. Okay. All right, so let's look at just a quick example. Let's determine the oxidation numbers for an example here real quick. The following compound. This is a wonky one. Let's do this one because it is kind of silly. Okay. So what we want to do is we want to determine what is the oxidation number for potassium, what is the oxidation number for oxygen. So going down our list, do we have any free elements? No. Do we have any monoatomic ions? No. So the most important thing here is the summation of the oxidation numbers has to equal 0. So that's going to be one of the most important factors here. Okay. Next rule, metals have positive oxidation states. So the first one we're going to look at is potassium. So each atom of potassium is going to have an oxidation state of +1. How do I know that? Well, potassium is a group 1 metal. It has 1 valence electron, and when it becomes an ion, it will lose that valence electron. It will give it away. That will give it a positive charge. So when in doubt, the charge of an ion and the oxidation state are sometimes the same, and in this case they are. Okay, so each potassium has a +1, and there's 2 of them. So potassium as a whole is a 2+. Okay, now we look at nonmetals. So nonmetals are less important. We determine oxidation state for nonmetals based on metals. Okay, so if potassium is a 2+, and whatever oxygen is, the sum has to be 0, right? It has to be neutral. These two oxygens together must have what sort of oxidation state? Yeah, it's got to sum to be a 2-. That way 2 plus -2 equals 0. So if each of the oxygens once added together is a -2, what must the oxidation number be on each individual oxygen? Yeah, it's got to be a -1. Okay. So potassium has an oxidation state of +1. Oxygen has an oxidation state of -1. Now that we've reviewed the rules for establishing oxidation states or oxidation numbers, now let's look at oxidation reduction reactions or redox reactions. So the substance that loses electrons, so across the chemical reaction, if it loses electrons, that's going to be oxidized. And one of the silly ways that we remember this is Leo the lion says grr. So Leo, our lion, lose electrons, oxidize. Leo the lion says grr. So reduction is the substance that gains electrons. So grr, gain electrons reduced. So that's just one silly way to remember. Leo the lion says grr. Lose electrons oxidized, gain electrons reduced. Another one is oil rig. So I've seen this one before too. So oil rig is oxidize, it loses, reduced, it gains. So same idea here. Oxidized is losing electrons. Reduction is gaining electrons. The last one that I like for reduction is the oxidation state, or the oxidation number will go down. So if the number reduces, so it goes from a 0 to -1, or it goes from +3 to +1. If the number gets reduced, that is a reduction. That's gaining electrons. That's another good way to remember it. So let's look at this chemical reaction and let's determine who was oxidized, who was reduced, and then maybe who stayed the same. So the first step is going to be establishing oxidation numbers. So we've got a carbon, we've got a hydrogen, and we've got an oxygen. So thinking back to our hierarchy list, rule number 1 is free elements have an oxidation number of 0. Boom, this guy right here is a free element. He's just all by himself, so his oxidation number is 0. Looking at CH4, so both of those are nonmetals, so we're all the way on the bottom of our hierarchy list. So not a free element, not an ion. Summation is going to have to be 0, so that is important. Not a metal, so we're in the non-metal list. So looking at this chart, which nonmetal is more important? So we don't have fluorine. Ooh, hydrogen. That's going to be the important one. Okay. So hydrogen atoms are going to have a +1 oxidation state. So this guy is going to be a +1. And then for this whole molecule to be neutral, each hydrogen is going to be a +1. There's 4 of them. So in order to be neutral, that carbon has to have a -4 oxidation number. So that sounds a little odd, but that's how it works out. That's how it shakes out. So let's go to the other side. Okay. So now I'm going to break oxygen up because I see it in 2 different places, and there's a possibility that that oxidation number might be different for both of those. So I want to just make sure that I break them apart. Okay. So let's look first at carbon dioxide. So again, carbon dioxide, that's a nonmetal and a nonmetal. So we go to our nonmetal rules. So it's not fluorine, it's not hydrogen. Oxygen is more important than carbon, okay? So in this case, each oxygen is going to have the oxidation state of -2. So oxygen is going to be -2. And again, there's 2 of them. So oxygen brings -4 to the table. So what's the oxidation state on this carbon? Yeah, it's got to be a +4 in this case. It's a +4. All right, let's go over here to water. So for water, again, it's a nonmetal and a nonmetal. So we've got hydrogens and oxygens, so not fluorine. Hydrogen is more important than oxygen, so we're going to establish hydrogen. Oxidation state is going to be a +1. There's 2 hydrogens, each with a +1, so this brings +2 to the table. So that must mean the oxygen is a -2. So in this case, both of the oxygens happen to have the same oxidation number, so that works out for us. Okay. Now we need to decide who's being oxidized and who's being reduced and who's staying the same. Well, hydrogen's the easiest one to look at. So hydrogen as a reactant had a +1 oxidation number. Hydrogen as a product had a +1 oxidation number. So that stayed the same. Like it didn't gain or lose electrons, so we can ignore that. Now we need to look at carbon and oxygen. All right, so oxygen had an oxidation number of 0. Now it has an oxidation number of -2. So to go from 0 to -2, that means it must have gained 2 electrons, gained 2 negatively charged particles. We also see that 0 to -2, the number goes down. So oxygen is GER, gain electrons reduced. Okay, I'll clean this up a little bit. So oxygen was reduced, or that's where the reduction takes place. Now let's look at carbon. Carbon went from -4 all the way to +4. So to go from -4 to +4, you've got to get rid of negatively charged particles. So in this case, it lost 8 electrons. So this is our Leo. So lose electrons, oxidize. So carbon reactant to carbon product is an oxidation or oxidized. Okay. So that's tracking oxidation numbers in a chemical reaction. And what you'll see in these slides is that it does the exact same process. Okay. And then here's just a prettier picture of those numbers. So why don't you guys go ahead and take a look at these 2 examples and see if you can determine who is being reduced and who is being oxidized. So pause the video, work it out, and I'll catch up to you. All right, so first example is pretty easy. So free element, oxidation is 0. Free element, oxidation is 0. Then we've got water again. So if you look at your list of rules, hydrogen is more important than oxygen. So we do hydrogen's oxidation number first. So it's a +1. There's 2 of them. So it brings brings a +2 to the table. So oxygen's oxidation number must be -2. Okay. So oxygen 0 to -2. That number is going down, so that's our reduction. And then hydrogen is 0 to +1. So that would be an example where he loses electrons. This is your oxidation, oxidized. Okay. So hydrogen's oxidized, oxygen is reduced. Okay, so over here to the second one, a little bit more to think about. So free element, hydrogen is 0. We've got phosphorus, and we've got oxygen. So those are 2 nonmetals. It turns out that oxygen is our more important nonmetal. So oxygen is going to have an oxidation number of -2. There's 2 of them. So oxygen brings a -4 to the table. So that means phosphorus must have an oxidation number of +4. Okay. Going to the product side. So we see one ginormous non-metal compound. So we got to do the hierarchy here. So the first one in the hierarchy is hydrogen. So hydrogen will have a +1 charge. And I'm just going to keep track of the total over here just to make things easier. So hydrogen has a +1 charge, and there's 3 of them. So that's a +3 that it brings to the table. Phosphorus and oxygen. So I don't really know yet what the oxidation numbers are going to do here. So again, I have to pick which one's more important and then assign the oxidation number. So oxygen is more important than phosphorus. So oxygen's going to have a -2 oxidation state. And then looking at the total, there's 2 oxygens. So he brings a -4 to the table. Okay. So this has to be a neutral compound, which means the addition of all of the oxidation states has to be neutral. It has to be 0. So right now I've got a positive 3. I've got a negative 4. So must the oxidation number on this phosphorus be in order for this total to equal 0. So the oxidation number on that phosphorus has to be a positive 1. That way we've got 3 minus 4 plus 1 equals 0. So oxidation on this phosphorus is a positive 1. Once you've assigned oxidation states, it's pretty easy at that point then to look at who's being oxidized, who's being reduced, and who's staying the same. So oxygen went from a -2 to a -2, so he did not gain or lose any electrons. So he's just kind of spectating in this case. Hydrogen went from 0 to positive 1. So that number went up, so he must have lost electrons. So this is going to be our oxidation. Phosphorus went from positive 4 to negative 2. So that number went way down. So he must have gained lots and lots of electrons during this chemical reaction. So that's going to be our reduction. And looking at the slideshow, that's exactly what we see. Okay. So that's your review for oxidation, numbers, assigning them, and then looking at redox reactions. This is a skill that you're going to need as we start to look at voltaic cells. Hope you guys found this helpful.